I'm Mercurides, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 11. Find the largest product of four adjacent numbers in the same direction in this 20 by 20 grid. The problem text suggests that there are 5 directions to contend with: up, down, left, right, and diagonal. However, a bit of careful consideration shows us that we only need to consider 4. At a given position in this grid, in principle, we can look in any of the 8 directions for a solution. That is, we can look in the 4 cardinal directions, up, down, left, and right, and we can also look in the 4 diagonal directions: up left, up right, down left, and down right. Now, let's consider one of these directions for a moment. Let's say we're looking at this position, and we choose to look at a sequence going down from the current position. We have 4 numbers to multiply, but this sequence can just as easily be viewed as a sequence of 4 numbers pointing up from a lower position. This is true in general. Every downward sequence of 4 numbers can be viewed as an upward sequence with a different starting point. Every rightward sequence can be viewed as a leftward sequence with a different starting point. And the same is true for the diagonal directions. A down-right sequence is just an up-left sequence by another name, and likewise for down-left and up-right. So even though there are 8 directions to consider, since multiplication is a commutative operation, we can eliminate 4 directions as redundant. Thus, we'll only consider the upward, leftward, up-left, and down-left sequences of numbers. Beyond that, there's no real clever trick here. This is a straight computation. We're going to store our 20 by 20 grid in an array, loop over it to calculate every possible product, and then take the largest. We're going to write our draft for this week in Java. Every Java program must be contained in a class. In our case, we won't be using any terribly fancy object-oriented features, so all of our class functions will be static. First, let's write some basic helper functions. We'll write 4 functions, one for each of the directions we're considering. Each function will take our input array and a starting position, and will multiply 4 numbers together, starting at the given position and moving in the chosen direction. First, our upwards function. Given our 2-dimensional input array, a row and a column, we grab the value at the starting position, then start decrementing the row value while leaving the column constant. This has the effect of giving us the value at the starting position and the 3 values above it. We multiply those values together and return the product. Our array consists of integers, but we cast the first value to a long integer before multiplying. While the result of multiplying 4 inputs would probably fit into a 32-bit integer in our problem space, we're being perhaps overly defensive and treating our products as long integers just to be safe. Now we do the same thing for left-facing sequences. In this case, we decrement the column while leaving the row number intact. For our up-left diagonal, which we call diagonal 1, we decrement both our row and column. And finally, our down-left diagonal, called diagonal 2, we decrement our column index and increment our row index. This gives us our 4 directions that we need to check. Now, we write our main function. In Java, the function that we'll execute when starting our program is a static function called main. In this function, we initialize a 2-dimensional array to the grid shown in the problem description. Then, we create a long variable to store the largest product we've found so far. We'll start this variable at 0, the smallest non-negative integer, to indicate we haven't found any results yet. Now we loop over the positions in our array. The array is a 20 by 20 grid, so our row and column variables will each range from 0 to 20. Inside of our loop, we have to be a bit careful. If we try to check each direction blindly, we'll run out of our array bounds fairly quickly. For example, we should only check our upward direction if our row number is at least 3. That is, if there are at least 3 numbers above us to check. So we check up if the row index is at least 3. We check left if the column index is at least 3. We check up left if the row and column indices are each at least 3. And we check down left if the column index is at least 3 and the row index is at most 16. In each case, we run the check and take the maximum of the result and the current best solution, storing that result back into our best solution variable. At the end of the loop, we print out the best solution overall. Now we have our program. Let's clean it up a bit. First, 2-dimensional arrays are nice, but we're going to need to reduce that to a 1-dimensional array for reasons that will become more clear in a few minutes. So rather than creating an array of integer arrays where each element is a row, we'll store all of our numbers in a single flat array and do some basic arithmetic to index into it. To facilitate our indexing, we'll write another helper function. This helper function, called getPosition, will take the array, a row number, and a column number. We know that every row takes up 20 elements, so the first row occupies positions 0 through 19 in our array, the second occupies positions 20 through 39, the third occupies 40 through 59, and so on. In general, if we want to access row n, then we want to look at the indices in our array from 20 times n to 20n plus 19. To get a specific position in our array based on a 0-based row and column number, we multiply the row number by 20 and then add the column number. And this is the Java code to do the same. Now we simply change all of our direct array accesses and our other helper functions into calls to this one helper, and we have another working program. Next, I'd like to simplify main. All of these constant bounds checks feel very ad hoc and awkward. It would be much easier if we could just replace all of the possible out-of-bounds errors with zero values, since a result of zero will never be our largest solution anyway. Let's write a new getPosition function that does bounds checks. If we give it a row or column number outside the range of our grid, we'll simply return 0. This will effectively poison our product, since the product of 0 with any number is still 0, and hence will never be our largest answer. Now we change all of our getPosition calls to invoke this new getPositionSafely function instead, and we can simply remove all the bounds checks in main, making it much more straightforward. The next thing we're going to do is make our array into a global variable. The array never actually changes, and it'll be easier down the road if we don't have to think about passing it around everywhere. Now we have a fairly simple program. Let's talk about our language of the week. We'll be writing this week's program in an assembly language, specifically the Netwide Assembly. An assembly language is a programming language that has a very close connection to the actual physical hardware of your machine. In most conventional high-level programming languages, we instruct the computer on what we want to do, and it produces instructions for the processor to actually do the work. For instance, we might write x equals y plus 1. Internally, the system may convert this into a move instruction to move the value of y to wherever x is being stored, followed by an increment instruction to increment the value of x. In an assembly language, we write these instructions directly, and we control what values are in the various registers available to us ourselves. The Netwide Assembler in particular is a popular open-source cross-platform assembler for the Intel x86 architecture, which is what most modern desktop and laptop computers run, so it will do fine for our purposes. We'll write an example assembly program in a moment, but first, we need to talk about register. x86 is a register memory machine, which means the data we're actively working with, doing math on, or comparing will be stored in one of a handful of machine registers. These registers are sort of like variables, except that they're global to the program and we have a finite supply of them that we have to manage. This is in contrast to a stack-based machine, where most computations are done on the stack, similar to the stack-based programming languages we've worked with in the past. We still have access to a call stack in x86 assembly, but we'll primarily be using the registers for computation and the stack for storage. There are 16 so-called general-purpose registers available to us in a standard x86 assembly program. These are RAX, RBX, RCX, RDX, RSI, RDI, RSP, RBP, R8, R9, R10, R11, R12, R13, R14, and R15. Though for our particular use case, we won't need any of the numbered ones, we'll manage just fine with the first 8. Each register can store a single 64-bit value, usually either an integer or a pointer to some location in memory. This is a good place to interject that assembly languages are often highly non-portable. I'm writing this on a 64-bit Linux machine. If you're running a 32-bit architecture, all of these registers will have different names and will be only 32 bits long. The program we'll write today will not work on 32-bit machines unless you modify it fairly heavily. Likewise, there are going to be some subtle differences if you happen to be using Windows this week, but I'll mention those when we get closer to that point. Now, although I call these general-purpose registers, they do each have common uses that many instructions are optimized to work with. For instance, RAX is the accumulator register, which is conventionally used to store a long-running sum or product of some data in a loop or larger computation. RBX is called the base register, often used to store pointers or addresses to large chunks of memory. RCX is the loop counter, and there are convenient looping instructions that interact directly with it. RDX is the data register, often used for overflow from RAX. For instance, if we multiply two numbers, the result will be stored in RAX, but if the product happens to be too large for a single 64-bit register, the rest of the value will be stored in RDX. RSI and RDI are more general purpose, though they're commonly used as source and destination pointers in string or array operations. RSP and RBP are respectively the current and base stack pointers. We'll be discussing these more in a moment. The 8 numbered registers have no specific designated purpose and can be used as needed to store arbitrary data. Finally, it's not uncommon in assembly code to work with smaller pieces of registers. Each of the general purpose registers can be broken down into smaller pieces. Let's consider RAX for a moment. This register consists of 64 bits. We can access the lower 32 bits using EAX. The lowest 16 bits can be accessed using AX. Finally, we can break down AX into 2 parts, the higher 8 and lower 8 bits called AH and AL, respectively. The same thing is true for RBX, RCX, and RDX. The other registers can be broken down, albeit with a slightly different naming convention, into 32, 16, and 8-bit pieces as well, though there's no equivalent to the higher 8 bits AH for those 12. Alright, let's write some actual assembly code. The first thing we'll write is a bits directive with argument 64. This informs the assembler that we're writing a program intended for 64-bit machines. It can usually figure this out based on other heuristic information, but just to be safe, we put it here anyway. Next, we declare a global symbol main. This will be the main function and the entry point to our program. We'll also assert the existence of a function called puts. More on that in a moment. After that, we start our data section. The data section is a collection of bytes whose initial values are stored directly in our program executable. These can be accessed and modified freely during the execution of our code. They're basically the global variables of our assembly program. In our case, we'll declare one global variable called hello string. We define its value to be a sequence of bytes using db. These bytes are the ASCII values of the characters in the string hello world. Finally, we terminate the string with a null or 0 byte. This is not the character 0 on your keyboard. This is a literal 0 value, or a sequence of 8 zeros stored in a byte. This is a C convention that will follow here. Our strings will be terminated by a null character to indicate that we've hit the end of the string. Once we're done declaring our global data, we switch over to the text or code section of our program. This is where the actual code of our program will be stored, and this is what the processor will run when we eventually execute our program. We promised the existence of a symbol called main, so we'll declare a label called main now. Labels in assembly work like they do in C# or whitespace. We can use them as the target of jump instructions or call instructions. For this simple example, though, we only need one label, main, which will be called as our program's entry point. Inside main, we do some stack shuffling. We'll talk about how to manipulate the stack soon, but for now, just trust that any label we write that's intended to be called as a function should start with these 2 lines. Now, we want to call puts. We asserted its existence a moment ago, but where does this puts function actually come from? Puts is a function defined in the C standard library, and we'll be using the libc implementation today. Libc is a collection of useful cross-platform functions available to C programmers. We're not writing a C program today, but we can still leverage these functions by linking our program against libc. So as long as we have access to libc, we can use puts. Now it's time to talk about how to call functions. Puts takes one argument, a pointer to a character array, so we need to know where to put that argument. There are several conventions for how to pass arguments to functions, and unfortunately, operating systems disagree on which convention to use. The system v ABI is used on Linux and Mac OS systems. In this system, the first 6 integer or pointer arguments are stored in registers. In order, we store them in RDI, RSI, RDX, RCX, R8, and then R9. If a function has more than 6 arguments, then we store the rest on our call stack. So, to call our function with one pointer argument on a system V machine, we simply put the argument in the RDI register before making the call. However, Windows uses a different convention. On a Windows machine, the first 4 integer arguments are stored in RCX, RDX, R8, then R9, with excess stored on the stack. So if you're running on Windows, you need to store the argument to puts in RCX, not RDI, before making the call. I'll be programming on Linux for today, so I'll follow the system V convention. We store the address of our global string in the RDI register, then call the puts function to actually print the string to the screen. At the end of our main function, we pop RBP. This is more stack manipulation boilerplate that we'll get to in just a minute. Finally, we return from our function, allowing the program to exit gracefully. This is a Hello World program written in x86 assembly. Let's discuss how to build it. For many of the programs we've written in this series, the task of running the code has been fairly trivial. We simply download an appropriate interpreter from whatever corner of the internet our language of choice crawled out of, and then we run it. Here, though, we have to do a bit of work to convert this assembly code into a runnable, native executable. NASM, the Netwide Assembler, is a command line tool. We specify that the format is ELF64, the 64-bit executable format used on Linux machines. Then we pass the file name. On Windows, your format will be Win64, and on Mac OS, it should be Macho64. Now this produces an object file, ending in the extension .o. This object file is not executable. We need to convert it into an executable, and we also need to link in libc so we have access to the puts function. We could do this using the system's linker, but we can also use GCC, the C compiler written by GNU. GCC will automatically call out to a linker with appropriate parameters to link in libc and set up our main entry point. This takes our object file. It also takes libc indicated by the -lc flag, and it produces an executable that combines the two and can be run on its own. Once we have that, we can run our executable from the command line just like we would any other program, and we see the string hello world. Now, let's talk about control flow. There's one more register I didn't mention before because it's sort of special and we can't access it directly. That register is called RIP. The IP stands for instruction pointer. RIP keeps track of where in the code we are as we run through all of our instructions. It's a pointer to an address in memory like any other, just that it addresses code rather than data. Normally, when an instruction like our move instruction finishes executing, the RIP register will increment automatically to the next instruction in our program. We can change that behavior by performing a jump. The simplest kind of jump is an unconditional jump. When our program runs an unconditional jump, it moves the instruction pointer, RIP, unconditionally to the point in code indicated by the jump target. This program will print out the string hello world forever. Every time we finish printing it out, we hit an unconditional jump that takes us back up above the puts call. Now, suppose we want to print this string not infinitely, but say 10 times. We can keep track of the number of times that we have left using a register. I'll use RBX for our counter here. It would, in general, be more idiomatic to use RCX for the loop counter, but RBX has the advantage that both Windows and Linux calling conventions consider it non-volatile, which means our puts call won't accidentally change this register. First, before we begin our print label, we put the number 10 into RBX. Then we begin our print label as before. We print out the string, then we decrement RBX. Next, it's time to do our conditional jump. We want to jump to the print label if the value in RBX is strictly greater than 0. Performing a conditional jump is typically done in 2 steps. First, we perform a comparison with the CMP instruction. The CMP instruction compares 2 numbers or registers and sets some flags in a special register called R flags, indicating whether the left-hand side is greater than, less than, or equal to the right-hand side. Then, we do a conditional jump. All the conditional jump instructions read R flags to check the last comparison and determine whether or not the branch should be taken. There are conditional jump instructions for all of the common comparison operators, including equal, not equal, less than, greater than, less or equal, and greater or equal. Additionally, the instruction is different depending on whether the inputs are signed or unsigned integers. In our case, we compare RBX to 0, then jump back to the print label if the comparison found that RBX was strictly greater than 0. This runs our homemade loop 10 times. On the 10th iteration, RBX will get decremented to 0, the conditional for the jump will fail, and the program will fall through to the last 2 instructions, which terminate our code safely. Now it's time to talk about functions. If you've written code in C, C++, Java, or really any mainstream programming language, you've probably heard the term call stack thrown around. It's time to learn what that actually means. When your program starts, one of the many things the operating system gives you is a call stack. This is a large chunk of contiguous memory that your program has total control over. Its size varies depending on the linker used, but by default it's probably a few megabytes large. Functions themselves are really just labels, identical to the labels we've been using for conditional and unconditional jumps. The big difference, though, is that when we make a regular jump, we have no intention of ever coming back. Sure, we might happen to end up at the same point later in the program, but we won't ever do so as a matter of course. With a function, we explicitly want to go to the function, execute some code, change some registers around, and then return back to exactly the point where the function was called. That means we need to remember where we came from. And that's what we're going to use the call stack for. At the start of our program, RSP points to a position on the call stack, and we can freely move it around, storing things and later accessing them. In fact, doing so is such a common task that there are instructions built just for it. The push instruction decreases RSP by the size of its argument, and then stores some data on the stack at the new position. Pop, on the other hand, moves a value of appropriate size from the stack into its argument, then increases RSP to compensate. In principle, here's what we'd really like to do if RIP was an ordinary register. This code won't run because we're not allowed to treat RIP like any other register. In this example, our function is called printHello. When invoked, it will print our hello world string to the terminal. To call the function, we would push the current value of the instruction pointer onto the stack. Then, we unconditionally jump to the printHello label. After printHello is done doing its work, we pop a value off the stack and into RIP, effectively forcing our program back to where we just called from. Since we can't directly modify the instruction pointer, the architecture provides us with specialized instructions to do exactly what we want in this case. To push the instruction pointer onto the stack and do an unconditional jump, we use the call instruction. And to pop off the stack and back into the instruction pointer, we use the evocative ret instruction, short for return. This will work, but it won't be very useful once we need to start doing more sophisticated things inside our functions. See, we're going to use the stack for more than just instruction pointers. We'll also be able to pass arguments to functions on the stack, and even declare local variables if we need to do so. But if we call another function inside of our special function, RSP might get changed or messed with. That's where RBP comes in. RBP is conventionally the stack base pointer. Whenever we start a function in assembly, we generally want to set RBP to the current value of RSP. That way, inside of our function, we can confidently access data that was near the top of the stack when our function started executing, even if that data may be somewhere else relative to RSP now. Of course, for this to work, we need to preserve the caller's value of RBP since they may be doing the same thing. Registers are basically global variables, so our function doesn't get its own copies of them. At the beginning of every function we write, we're going to push the current value of RBP onto the stack, preserving the caller's base pointer. Then we'll move the current value of RSP into RBP, setting up our own base pointer so we can access arguments and local variables freely. Then, at the end of our functions, right before returning, we pop the caller's RBP, giving them back their original base pointer. Let's see how we can use this to pass arguments to a function. Let's write a version of print hello that takes a single argument on the stack, indicating the number of times to print the hello world string to the terminal. To call our new print hello function, we'll first push the number 10 onto the stack, indicating the number of times we want to print our string. Then we call it just like before. We'll get to the implementation in a moment. Finally, when we're done, we need to clean up this extra value on the stack. We pushed a 64-bit integer onto our stack, so we need to pop 64 bits worth of data. We could use pop and put the number into a register, but since we're planning to just discard it, that would be a waste of a register. So instead, we can simply add 8 bytes, or 64 bits, to the value of RSP, which functions the same as popping the value. Now, let's take a look at the inside of the function. Before we dig in, let's analyze what our call stack looks like at this moment. RSP currently points to the top of the stack, like it always does. Currently, the top of the stack holds the instruction pointer for main, which is what our red instruction will eventually use to determine where to jump back to. Below that, we have our argument 10 that main pushed onto the stack. Our BP at the moment points to some other undetermined place on the stack that main cares about. Print hello doesn't know or care exactly what that position is. We push the current value of RBP onto the stack. This decreases RSP by the size of a machine word, or 8 bytes on a 64-bit machine. Next, we move the current value of RSP into RBP, making our new RBP point to the old value of RBP on the stack. Finally, we're going to push RBX onto the stack. This is because we'll use RBX as our loop variable in just a minute, and if the caller had something important in RBX, we want to preserve that value as a courtesy to them. Now, we want to load our argument into RBX. Our argument is 2 machine words below the position RBP is pointing to. And a machine word is 8 bytes. So we want to take the value at stack position RBP plus 16 and move it into RBX. We can use a special indirection syntax to do this in a single move instruction. We use brackets around a register like RBP to indicate that we don't want the value of the register, but instead want the value pointed to by the register. This is essentially a pointer dereference, like the unary star in C and C++. In addition, we can add or subtract constant values to get something that's offset from a register by a certain amount. All in all, our instruction looks like this. And it reads, take the value 16 bytes below RBP on the stack and move it into RBX. Our loop looks just like it did in our earlier program. We print our hello string, then we decrement RBX, compare it to 0, and jump if greater. At the end of our function, we pop RBX to restore the caller's value. Then we do the usual end of function routine, popping RBP to restore the caller's value, and then returning. Now we know how to write functions. When we write more sophisticated programs, we'll adopt a calling convention sort of like cdeclare, for simplicity. That is, we'll pass all of our arguments on the stack. We expect the caller of a function to clean up the stack after the fact. Any return value from a function will be given in the RAX register. And for simplicity, we'll expect the function to preserve any registers it wishes to use other than RAX. We have all the tools we need. Let's solve our original problem. First, our header. This will look like most of the programs we've seen so far. We're writing a 64-bit program, which has a global function called main, and we'll use an external function called puts. Then our program data. We'll load our grid into memory as a large global array called, fittingly, array. Since all of our numbers are small, we store them in an array of 8-bit values rather than using 64 bits for each one. Next, we'll declare a string variable which is initially all null bytes. We'll use this as a helper variable to print out the result at the end. Now we get to the actual code. The first function we'll write is our getPosition function, which does not check bounds. It takes 2 16-bit integer arguments on the stack and returns a 16-bit integer in RAX, padded with zeros to fill out the 64-bit register. Inside this function, we do our usual function preamble. Then we push the registers we're going to use in this function, those being RBX, RDX, and RFlags. Arrays are stored contiguously in memory, so we put a pointer to the start of the array in RBX. Then we add the row number times 20 plus the column number to RBX. Finally, we get the 8-bit value from the resulting pointer and put it in AL. We zero extend AL into RAX with the MoveZX instruction, and now our result is in RAX. To end our function, we pop RFlags, RDX, and RBX in the reverse order we pushed them. Then we pop RBP and return. Next, we'll write the safe variant of this function. GetPositionSafe we'll call getPosition if its arguments are in bounds, and will quietly return 0 otherwise. After our function preamble, we push RFlag, the only register we'll need here aside from RAX, which is caller saved under our convention. We load our 16-bit row number into AX and compare it against 0 and 20. If either comparison fails, we jump to our out of bounds label, which we'll write in a moment. Then we do the same to our column number. Finally, if we haven't jumped to an out-of-bounds label, we push the row and column numbers again and call getPosition. Then we clean up our stack and jump to the end of our function. On the other hand, if we do jump to our out-of-bounds label, we set RAX to 0, indicating a default return value of 0, and move on to the end of our function. In either case, at the end, we pop rflags and RBP and return. Our next function is not one we wrote in Java because it was trivial with Java's high-level syntax. This function will take 4 16-bit integers, multiply them all together, and return the result as a 64-bit integer. The implementation is fairly straightforward. We accumulate a product in RAX and move several values into RDX to do multiplication. One slight quirk of multiplication is that unlike addition and moves, it always multiplies its argument by RAX, so we have to have the left-hand side in RAX. Additionally, it stores the result in both RAX and RDX, with the most significant bits in RDX. In our case, our numbers won't be large enough to need more than 64 bits, so we'll simply ignore the higher bits and use RAX. Next, we write our for-directional function. We have a safe way to check a single position, even if our input might be out of bounds. So our directional functions need only get the 4 positions and then multiply them via our doProd function we just finished. We start with the upward direction. We write our preamble, then we push the 3 registers we'll be using. We get our 2 arguments. We'll store the row number in BX and the column number in CX. Next, we get the position we're looking at. We push the result onto the stack. We won't use that particular stack position for a bit, but the value can sit there patiently for as long as we need it to. We decrement our row number and repeat, pushing the new value onto the stack. Do that 2 more times, and now we have 4 inputs lined up on the call stack. We invoke doProd, which takes 4 16-bit inputs on the call stack and returns its result in RAX. To clean up the stack, we add 8 to RSP. We pushed 4 values onto the stack, and each value was 16 bits or 2 bytes, for a total of 8 bytes. Our product is in RAX, so now all we have to do is clean up after ourselves. We revert rflags, RCX, and RBX, then pop RBP and return. Now we do the same thing for the left direction and the 2 diagonal directions. In each case, the only thing that changes is what we do to BX and CX in between the getPositionSafe calls. Our next function is a max function, which takes 2 numbers and returns the larger of the 2. Java had this built in, but in assembly we'll write it ourselves. It's nothing fancy. We take our 2 arguments and put them in RBX and RCX. Then we compare the 2 registers and go to one of 2 labels. If RBX is bigger than RCX, then we move RBX to RAX and arrive at the end of the function. If RBX is smaller than RCX, then we move RCX into RAX and jump to the end of the function. In code, the implementation looks about like what we've done before, just with slightly more complex control flow. Finally, we have our main function. Our main function consists of 2 loops, one nested inside the other. For the bulk of our main function, we'll keep our running best product in RBX. We'll use CX to store our column and DX to store our row. And we'll use RAX for temporary storage during calculations. Alright, let's get started. We initialize all of our relevant registers to 0. Then we enter our outer loop by resetting DX, our row number, to 0. We enter our inner loop and we call the 4 directional functions using CX and DX as arguments in each case. Each time, once we've called the function, our result ends up in RAX. So we push RAX, our function result, and RBX, our current best value, and we call max to store the new best product in RAX. Finally, we move RAX back into RBX where we're keeping our maximum product stored. At the end of our 4 directional function calls, we increment DX and repeat the inner loop until DX hits 20. When DX finally hits 20, we increment CX and repeat the outer loop. Finally, when CX hits 20, we exit our outer loop. We push our result and call L to string, then we puts the result of that, which outputs our best product as a number. Now, I haven't shown you L to string yet. This video is already fairly long, so in the interest of brevity, I'll simply give the code for now. I'll be publishing a companion video that goes into the details of this last function, and we'll write a few more example assembly programs as well. Until then, this solves Project Euler problem number 11 in Netwide Assembler. Tune in next time when we solve problem 12 in this language. Pronunciation is left as an exercise to the reader.